Here I am inspired in the beautiful city of Medellin Software Valley. The framework presented in this video is based on a two-part artificial intelligence autonomous vehicle research and development engineering prototype. This segment of the intelligent vehicle, part 2, presents the mathematical algorithms for the LIDAR system, LIDAR system, which includes the software models for the LIDAR light detection and ranging system. Light detection and ranging LIDAR technology is key used in this specific application to detect and to map surrounding objects. As illustrated in this presentation, the project performs extremely well with the adaptation of the LIDAR system, which provides both excellent range and high resolution, and it is combined with data from other sensors. I will talk about these sensors later on to accurately represent the vehicle's environment. So, LIDAR technology is less sensitive to field lighting conditions than camera sensing because it actively illuminates targets at infrared wavelengths. Therefore, LIDAR, L-I-D as in David, A-R, relies on the time delay between an emitted and reflected light pulse. It is simplest implementation. A pulse of laser light is emitted, and the resulting reflection from the scan object is detected. As a result, the distance to the detected object can be easily computed because it's represented by half the round-trip time delay, which is formulated as R equals to C over 2 times TOF, where R is the distance to the target, C is the speed of light, 300,000 kilometers per second in vacuum, and the time of flight, TOF, is the total time elapsed between the emission and detection events. The LIDAR process is repeated to scan the surroundings, and the raw data are processed to create a point cloud. Thus, the point cloud is a set of data points representing a three-dimensional shape or object. In the case of the LIDAR, it refers to the data points representing the objects from the scan space. So, the larger the detection range, the greater the time needed to produce the map, because the laser pulse will have to travel a longer distance because of the simplicity of the pulse-based LIDAR detection system. Now, we can apply continuous wave LIDAR, which is different than the pulse LIDAR. It uses either amplitude modulation or frequency modulation of the light source. In amplitude modulated continuous wave LIDAR system typically operates at a wavelength of 905, 1300, or 1550 nanometers. So the laser with a wavelength less than 1400 nanometers can damage the human retina. To the average power must be kept below the level required to comply with eye safety standards. In the LIDAR architecture, the transmitter in the transmitter, the pulse is generated and amplified by the laser driver. The resultant laser beam is then transmitted through the optics. In the receiver, the reflected light signal is detected by the photodiode, which produces a current proportional to the return signal strength. The current signal is converted to a voltage by a transimpedance amplifier, which has typically implemented as a discrete component outside of the system-on-chip architecture. The interface between the photodiode and the TIA, photodiode and the TIA, the transimpedance amplifier, is critical because it impacts the LIDAR range precision. So the LIDAR implemented in this design uses light-precise laser pulses to map an underlying object or the terrain, that is the Earth's surface. The laser is pointed on an object surface or the terrain, and after hitting the surface, reflects back. Mapping and 3D drawings of an object surface or terrain is quite simple. Every reflection of light is composed of thousands of individual beams. These beams or patterns vary in distance. Each one is nearly 10 centimeters apart. So the scanner picks all of this information. Therefore, the time and distance it takes for these beams to occur are recorded by the scanner. The distance between the object and the light source is calculated by using the recorded time and the speed of light. So the LIDAR communicates with an external controller via the I2C bus protocol with a pulse width modulation PWM output for the I2C. The data, the SDA data, and SCL, the clock pins, are used for the pulse width modulation. The mode pin is inserted which places the sensor in analog input or analog output mode, and as a result, each distance corresponds to an analog output value that must be sampled by the analog to digital converter, which is the ADC, at the host side, at the CPU side. And then it will take the data using the I2C protocol. So the architecture is fundamental. It connects the sensors to the I2C bus wires, and it wires it with the main CPU, central processor unit, the I2C pins, which are located in their respective ports. They are also present at the top of the header. The LIDAR design presented in this system methodology And as you have viewed in this video, includes the I2C bus general library, that is the wire.h, in the CPU sketch, followed by the LIDAR light library. An instance of the LIDAR light library is created. Now, in the setup function, when we initialized the serial monitor and started it at 9600 bits per second, the define I2C and a communications protocol. So in this software algorithm, the loop function is where we measure the distance. Two different functions are executed and the basis of the condition. So one function calculates distance without bias, and the other function uses bias. Therefore, the sensor's calibration is done in the function without bias. So as you can see in the software models presented in the video, the calculated distance is displayed on the main CPU subsystem serial monitor. A 10 millisecond delay is used after every scan to prevent any crossover or collisions. Now, based on the software principles and the mathematical algorithms, now I classify objects with the help of dots to do so. However, the LIDAR that can scan an entire area from center point is required with the LIDAR used in this specific application. It's only possible to calculate the distances. Higher resolution LIDARs can also calculate the angle of light from a reference point, and the angles and distances based on the terrain are then three-dimensional representations. The artificial intelligence autonomous vehicle is a project that has been segmented in two parts. I have presented part 1 in a previous video, and this is obviously the culmination of part 2 of the artificial intelligence autonomous vehicle. Okay, now let's talk about the artificial intelligence autonomous vehicle software LIDAR scripts. The software algorithm methodology is described in this project as I have illustrated in this video. So, first include the software serial.h file. Then include the tf mini.h file. Now let's set up the software serial ports. In the void setup of the script, initialize the hardware serial ports, that is the serial debug port, and serial begins at 115200. Wait for serial port to connect the USB port. Then initialize the data rate for the software serial port. TF mini LIDAR baud rate, initialize the mini LIDAR sensor. In the software script, now let's set up the void loop. take the LIDAR distance measurement. Display the LIDAR measurement, such as distance and signal strength. Now wait some time before the next measurement. The main LIDAR sketch code is based on the RP LIDAR driver library. So create the LIDAR driver instance. Then define the RP LIDAR motor, that is the pulse width modulation, to control speed of LIDAR motor. Now let's set the void setup. Bind the LIDAR driver to the CPU board, that is the main CPU board. Now, as I have illustrated the software algorithm in this video, let's take the void setup. The if statement sets the LIDAR waypoints, such as distance value, angle value in degrees, and accuracy of the measurement, that is the LIDAR measurement. Then set up the else statement to stop the LIDAR motor.